So today I wanted to talk about periodic orbits in Hamiltonian and near-Hamiltonian systems. So first I'll start with a bit of a recap and motivation. So you might recall that in a Hamiltonian system, which is the physical interpretation being that energy is conserved, the only fixed points would be hyperbolic saddles and periodic orbits. In fact, you would have lots of periodic orbits because, as you can imagine, if you have some fixed point with like one periodic orbit around it, then if you go slightly away from that, like energy is still being conserved, so you're just going to follow like a contour of slightly lower energy, for example, or slightly higher energy. So I guess the motivation is this question, like if we perturb a Hamiltonian system, then you might imagine something like this happens because energy is no longer being conserved. There's no reason for us to continue along the same contour and have a periodic orbit. So yeah, most of the periodic orbits might be destroyed. And so we want to find out whether some remain and which ones. So yeah, this is a bit of an illustration of that. So, okay, well, I've numbered this wrong, please ignore that. We're going to look at what a near-Hamiltonian flow is. So, first of all, we'll look at, what the Hamiltonian flow is. So a Hamiltonian flow is a flow of this form, but with, epsilon being 0. So basically, well, the system's defined to be Hamiltonian with x dot being equal to the y partial derivative of h, and f2 being negative of the x partial derivative of h. Yeah, and so if we can find an h that satisfies this when epsilon is 0, then we have a Hamiltonian system. In this case, as I said before, the trajectories, for example, might be periodic orbits. They would lie on the contours of h, so curves of constant h. And the POs would lie on the closed contours of h, because, well, that makes sense, and there would be many POs. But we're more interested in what happens when the system is near Hamiltonian. In other words, instead of having an actual Hamiltonian system, we have like this small perturbation away from it with this epsilon term, with epsilon small, so small but positive. So now we would write h dot, the time derivative of the Hamiltonian, as being this, where hx and hy are the partial derivatives of the Hamiltonian of the the system without the epsilon term. Right, so to find hx and hy, we're ignoring the epsilon term and treating the system like a Hamiltonian flow. To find h dot, this is h dot of the full system, including the epsilon term. And in general, some of these, the Hamiltonian terms cancel out, because in a Hamiltonian system, h dot is equal to 0. So we're left with this term, which comes from the perturbation.
Sorry, so the hx and the hy, are those the partials of the original or the perturb?
The original system.
Okay, yeah.
Yeah. And because the original system without the perturbation is Hamiltonian, which, in a Hamiltonian system, energy is conserved, so h dot would be 0, those terms cancel, and we're only left with the perturbation term. So you could just do this in exams. It doesn't take that long, but if the algebra is messy, like an important shortcut and to avoid mistakes could just be to remember this formula. It does come up quite a bit, so F1G2 minus F2G1. So now we're going to say, call the PO gamma. So along gamma, energy is conserved, so in the original system, right? So this integral is going to be equal to 0. But more usefully, we can rewrite this as a time integral. And because we know what h dot is, we can substitute that in from the previous bit. So again, epsilon times f1 g2 minus f2 g1 dt, that's equal to 0 in the original system. And so, hold on. Sorry, not in the original system. Yeah, so this is in the Near-Hamiltonian system, sorry, so in the perturbed system. Yeah, so in order for us still to have a PO, for this PO to be preserved, well, we must have this relation holding. In other words, the change in the system, including the perturbation, is still 0 over one period. So I guess a consequence of this is that the PO cannot lie entirely in a region where this thing is single valued, because then clearly the integral would not be equal to 0. That's noting that this cannot be equal to 0 in the first place, because we're in a near-Hamiltonian system and h dot cannot be equal to 0. Does that make sense?
Yeah.
Okay. Yeah, so I guess that's just a good integral to remember. Next thing is the energy balance method. So the idea here is to estimate the change in the Hamiltonian of the full system by considering the change in the Hamiltonian over contours of the Hamiltonian system. Sorry, of the Near-Hamiltonian system. Yeah. Okay. So this is a little picture. So we have this PO gamma 0 in the unperturbed system, and let's say it has period t0. Then we're going to perturb the system, and if we started at some point on the PO, we're going to go around by one period, and we're going to find out how much the energy changes. And so if the energy, right, does change, then that means it's not a PO, right? If the energy doesn't change, like if there is a 0 of the change in energy, given some, starting position, then we know that, there might be a PO. Yeah, I put a note here to remember that although I've drawn the blue and the black trajectories on the same, together, they are actually not part of the same system. So I've just drawn them together so that you can see what the difference is between them more easily. But yeah, the black trajectory is in the unperturbed system, and the blue trajectory would be in the perturbed system. So the way we would estimate the change in the energy would be, well, again, it follows a very similar path. We're going to say that the change in energy over the perturbed trajectory is in the integral over one period over this trajectory of the change in energy, which then we can rewrite using the previous expression that we found, which is epsilon times f1 g2 minus f2 g1. And because we've chosen epsilon to be small, you can convince yourself that the period along the perturbed trajectory is approximately equal to the period along the original trajectory. It's off by terms that are order of epsilon. And similarly with the trajectory itself, because we've only perturbed it by some term that's order of epsilon, the kind of the distance at any point between the two trajectories is going to be order of epsilon. So because of that, we simply rewrite the bounds of the integral and we rewrite the curve that we're integrating over. So now we can integrate over something that's known. We know the original PO, and we can find that by finding contours of constant energy in the Hamiltonian system. And we can also find the period. So now we have a known integral that we can integrate. And it's an approximation of the change in energy. That's important because we don't account for terms that are order of epsilon squared. However, it's still useful to us because it tells us that, even though it's a rough approximation, that we have some error. If we have, if we plot the change in energy over the energy level, then if we have something that we call a robust zero like this, where, even if we're off by order of epsilon squared, we'll still have a zero, then we know that there is a PO that survives at approximately this value of H. Whereas if we had something like a double root, this does not necessarily imply that there is a PO because it's an approximation. So for example, if being off by order of epsilon squared could mean that this actually looks like this, which would mean there is no PO, right?
Mm-hmm.
So there might not be a PO there, but there is definitely a PO here.
Right.
So yeah, this is the type of zero we're looking for, a robust zero. Or you could call it a simple zero as well. Okay, so the next thing that we can do is something called Floquet analysis, and this is actually a different thing. The picture looks similar, so I want to explain why it's different. Floquet analysis is analyzing the stability of the PO itself, so in a fixed system. So given some system, I have a PO. What happens if I start from a point that's like slightly away from the PO? Like, am I going to get near the PO or am I going to go away from the PO? Whereas energy balance, as we just discussed, is what happens when you perturb the system itself, not when you perturb a point away from the PO. So hopefully that's clear. So this picture basically says, if we start with, okay, we have this PO, right, in our system. We're not going to perturb the system, it's just a system, and we have a PO. If we start with a point that's a distance epsilon away from the PO, let's call it x naught, and we follow the forward trajectory for one period, t. So I'm following forward trajectory, I'm going to go this way. I should probably put some arrows on this. So we're going like this. How much does the initial perturbation grow or shrink? So that's kind of why I've drawn, epsilon and lambda epsilon, because, yeah, so lambda would just be like the growth factor, or well, the shrink factor of the initial perturbation. So clearly, if lambda is greater than 1 here, then the perturbation grows, and if lambda is less than 1, then the perturbation shrinks. And this might start to make you think of eigenvalues, which is indeed how we're going to approach this topic. So we're going to have to go through a bit of a lengthy general derivation. However, I think, again, although the general derivation is quite necessary in this case, I would say that you understand it better once you do an example. So I'll go through this bit quite speedily, and then we'll look at an actual example. So yeah, suppose we have, some initial value problem, the system with a PO with period t, and let's say that we write the PO as big X of t. By period t, well, that just means that, well, if you go around by one period, you end up at the same point. So we'll consider a small perturbation from the PO. We're going to call it eta. And yeah, we literally just take the derivative of x so that we can then use multivariate Taylor's theorem to expand f here for small eta. So we literally expand this thing. Again, I'll skim through this quite quickly. We expand it to the first linear term, and we neglect nonlinear terms. And we notice that what we have here, although it's written as a dot product, is actually matrix multiplication, because grad of f here is going to be a matrix. So there's just a few little bits of I've noted down what happens, and you define this matrix A to be the matrix you get from differentiating the ith element of F with respect to xj. So yeah, as I said before, you'll get matrix multiplication. You introduce some mapping capital Phi of T, and you essentially get an ODE here, which has a standard solution. From this, you would, hold on. Yeah, the standard solution includes the definition of script A, or I don't know, just fancy A being this. And because the PO was T periodic, and that carries through throughout the calculations, you find that A is also T periodic. And so in the end, we get this. And remember that eta was the perturbation, the initial perturbation, or eta of 0 was the initial perturbation. So the key point here is that we've shown that whether or not the perturbation shrinks or grows depends on the eigenvalues of this matrix phi. Yeah, and these eigenvalues are going to be called Floquet multipliers from now on. So we'll let the lambda I be the non-trivial eigenvalues. So we're guaranteed one eigenvalue, which is just 1. Then we're going to have that if there exists an eigenvalue with modulus greater than 1, then the PO is unstable. If all of the eigenvalues have modulus less than 1, then the PO is asymptotically stable. And if all of the eigenvalues are not equal to 1, then the PO is hyperbolic. By not equal to 1, I mean, well, if the first two already don't hold. So we have some greater than 1 and some less than... Sorry, hold on, what did I mean by that? So, I think I meant they're all equal to 1. Yeah. Then the PO is hyperbolic because basically, because we've only looked at the linear terms of the system, the linear perturbation. Where did I get it? Yeah, so I've discarded the nonlinear terms. It could be, linearly hyperbolic, it could be uncertain when you look at only the linear terms, whether it's stable or unstable. So in this case, you would have to look at higher order terms. Since we've now defined the Floquet multipliers to be the eigenvalues of this matrix, we'll also define the Floquet exponents, and we can define them in terms of the eigenvalues of the matrix. But also, well, equivalently, we can define the Floquet multipliers as the exponent, or the exponential of the Floquet exponents times the period. So, yeah, as I said, this derivation looks quite messy, and it's just not very well explained without an example. So we're going to look at what it's like in practice, for example. No, sorry. We're going to look at an easier method in practice for R2 specifically. So you might recall from before we had this equation. Again, this derivation is not that important. We're going to take the solution, the general solution of the ODE, and then we'll take the determinant of both sides. And there's this property that, I don't know, it says recall. Honestly, I didn't recall it. But there's this cool property about the determinant of E to a matrix being E to the trace of the matrix. If we assume that this matrix M is diagonalizable, then we can do this simplification. And it turns out that we get the determinant of this diagonal matrix, which is simply the product of e to the eigenvalues. Okay, I should probably write this out a bit more. So this is the product of e to the eigenvalues, which is of course equal to e to the sum of the eigenvalues. And so if, as we say, we are in R2, if, sorry, okay, never mind that. Yeah, so as I said, we are in R2, and as I said before, one of the eigenvalues is guaranteed to be 1. So in that case, we can find the second eigenvalue through the calculations I've shown here, and it turns out that it is this, and this gives you the non-trivial Floquet multiplier.
Sorry, how do you get that other one?
This. Yeah, so it's from this calculation here with this trick, and yeah, so this part's quite easy to understand. You just use determinant properties, expand this thing, and you should it's equal to this, and then I believe what you do is, yeah, so we're using this property to rewrite this thing up here. And so from here, we're actually jumping down to there.
Okay.
Yeah, so as you can see here, we have like, this is E to some matrix, and we've changed it to E to the trace of some matrix.
Yeah, okay.
Yeah, so that's what we're doing. And because we're working in R2, that just simplifies to this, because we know that one of the eigenvalues was 1.
What simplifies to what?
This trace here, so integral of the trace. So the trace of this, Yeah, I'm gonna have to look at that again actually, because I think I haven't really cared too much about this, because the derivation doesn't seem to come up at all in exams. Yeah. But I will look at it and have a look. But I think the main thing to remember is this thing here. Okay, anyway, so let's just assume we have this for now. We have a non-trivial Floquet multiplier. And so in a 2D system, this will determine whether something is unstable, stable, or non-hyperbolic according to these relations. Which makes sense, of course, since the eigenvalue tells you, whether you're going away from the origin or towards. Another thing is in Rn, this thing is still useful. So yeah, now that we have that this exponential thing is the product of all of the eigenvalues. Of course, the eigenvalue of 1 doesn't really matter. So we have now a necessary condition for stability, because for stability to happen, we need all of the eigenvalues to have modulus less than 1, which would mean that clearly the product of all of the eigenvalues has modulus less than 1, which would imply that this integral would be less than 0 due to this equality. Yeah, is that true?
Yeah.
Yeah, okay, good. So we'll look at an example, and I think this will go a lot better than the derivation. So with this system, we have a PO at r equals 1, and the theta dot along the PO is equal to 1, which means if we integrate this, the period is going to be t. So yeah, so then clearly, sorry, not the period, theta is going to be equal to t, which means that the period is equal to 2 pi. So if we perturb from this PO, let's consider a perturbation, R is equal to 1 plus delta of t, and theta is equal to t plus epsilon of t. So yeah, this is a lot more straightforward than the derivation. We simply take r dots, and we also differentiate the right-hand side with respect to t, and we get this thing, which we can then simplify to negative 2 delta plus order of delta squared. And then we can solve this ODE to get delta of t is equal to some arbitrary, initial perturbation delta of 0 times e to the minus 2t.
Sorry, I have no idea what is why is theta equal to t?
Why is theta equal to t? Because theta dot is equal to 1 on the PO. So I've skipped all of the workings to find the PO, but the way you would find the PO is just to find out when r dot is equal to 0, and that happens to be at r equals to 1.
Right.
And then plugging that into theta dot on the PO, we have theta dot is equal to 1.
Oh, okay.
Yeah. But I've just skipped those workings, sorry. Yeah, so this bit's all fine, right?
No, it's too fast for me. I didn't follow.
Okay, so yeah, we've considered a perturbation. We've just constructed it. We've said, in the r component we perturb it by delta, the theta component we perturb it by epsilon along the PO.
Okay.
So then we would take the derivative of r, with the goal being that we want to find the rate of change of perturbation.
Yeah.
So yeah, we do this. ddt of 1 plus delta t is equal to delta dot. But also we have oh, I do not know why I've written it in this way. I should probably write it like this. Sorry, so this is more clear. So r dot is equal to this thing, but r dot is also equal to r times 1 minus r squared. But we know that r on the PO, the perturbed PO is 1 plus delta, so we just plug that into the equation for r dot.
Yeah.
To get this. And then we just expand and we get this to the leading order. Yeah, and then that's just an ODE that we can solve. Does that make sense?
Yeah, okay. So this seems very different from the technique from before, so I'm just confused.
Oh, which technique?
Well, it
the general derivation. Yeah, that's what I mean. I had to look at this a few times before I realized that this was actually describing that method, which is why I don't really know. I didn't understand this in lectures either because it just seemed like, what am I doing, right? I think it's just all of the notation and generalizing it for n dimensions and saying you got this matrix and then you have to integrate it in general. It just makes it overly complicated. But essentially the step that this maps to that we just talked about is we're writing this perturbation. So our e to t in the example just now was, to r we added delta t and to theta we added epsilon of t. So that was this step. And when we took the derivative, we were doing this next step. And instead of Taylor expanding, because we're not working in multivariate, we dealt with each variable separately. We dealt with r and theta separately, basically. So we didn't have to do any multivariate Taylor theorem. We just, literally, we just rewrote both sides of the equation, equated them, and then solved the ODE, which actually gets us up to this step. So this is where they've solved the ODE. So we've already gotten to here, but it doesn't feel like we've done any of this because this is just in my opinion, completely overcomplicated.
Um. Okay.
Yeah, we've literally gotten to this stage. It's just that they've done, instead of solving the ODEs for each variable separately, they've kind of just convoluted it into one big matrix and then tried to solve it in one go. Sorry, I shouldn't use the word convoluted like that. But do you see what I mean by this is like overly complicated? It is exactly the same thing, I promise.
No, we need to look at each step and say, like how, like why have we not done it? Like,
What do you mean why have we not done it? We have done all of this, is what I'm saying.
Okay, how have we done it?
So we didn't need to introduce this mapping because we're working in 2D, and the ODEs for R dot, sorry, for R and theta, both of the ODEs were just like explicit. They were obvious. Like we didn't have to do any strange mapping to justify this. It's because they're working in, like in a general case of n dimensions. I guess just to like add rigor as well, they've had to define this thing so that when they integrate the ODE, they can say they have this.
Okay.
Like we don't actually need a 5 basically, because we're just like working with the two equations almost separately. Yeah, so just to like recap, what we've done here is we've like done the perturbation, we've added our e to t, and then we've differentiated the whole system. Well, in this case, we've only done r first, but then later we will do theta. So you do the same thing with theta. So at this point, we have, what we would have arrived at the end of the multivariate Taylor expansion. But we didn't have to do any of that because we could deal with theta dot and r dot separately. The point is, right, after okay, maybe it'll help to go to the next step and then look back. So when we've solved the ODEs for delta and, sorry, I don't know why I called it ether, delta and epsilon, we end up with delta and epsilon in terms of the initial perturbations, delta naught and epsilon naught.
Yeah.
Which we can then write in matrix form, okay? So now we have this 5t. So if we jump back to the general derivation, we basically have, hold on, where is it? Okay, I think I skipped a step here. Yeah, so I kind of skipped something here. Like, we also have this. Yeah, it's just, yeah, that, I'm not sure where exactly that was actually. Yeah, so it would have been after integration, so I guess it would have been here. Yeah. Yeah, I won't lie. I mean, I don't completely follow this bit, but I can see like the parallels between how to apply it in practice and this general derivation. Yeah. I think the A comes about because they haven't really they've defined A, like special A here in terms of like the other A. But the things we're not really working with matrices anyway until after we've integrated, until after we've solved our ODEs and then we write it in matrix form, whereas they were working in matrix form the whole time. So I guess the structure just looks a bit different, but I'm not entirely sure why.
Yeah, okay.
Yeah. Anyway, the point is we've like done this integration step to solve the ODEs and we arrive at something of this form. which is this. So here we've literally just transcribed the coefficients in to the matrix. So yeah, now the point is literally find the eigenvalues of this matrix. So the eigenvalues are, well, we have 1, the trivial Floquet multiplier, and we also have the non-trivial Floquet multiplier, which is e to the minus 2t, where the period is equal to 2 pi. So that's e to the minus 4 pi, which is less than 1. So then we have a stable PO.
Okay, yeah.
So yeah, in practice, it's kind of a one-page thing. It's not like ridiculous matrices and having to solve matrix ODEs.
Okay, so can we see why that matrix, like why that's phi, like why that corresponds to phi in the derivation before? Because it's like saying eta is equal to like phi times eta of 0.
Well, phi is just the matrix that maps the, yeah, I can explain this actually. So we define phi, right, to be the mapping of the initial perturbation to the perturbation at the time t. So yeah,
okay.
it is the same thing. It's the same phi.
Yeah, okay.
I hope that was convincing enough. Okay, the alternative approach, which is the last thing I want to cover, is we could just use the divergence test instead. So this comes from the final bit of this proof here, where we say that the eigenvalues of phi are actually, well, in a 2D system, are just 1 and e to this integral.
Mm-hmm.
So instead of doing all the work to find the eigenvalues, like find the matrix, find the eigenvalues, and then find stability, we could have just plugged in the system into this integral. So remember that f is equal to x dot, or the vector x dot. So we could have just done that in the first place. I guess the only difficulty of this is remembering the formula for divergence in polar coordinates, but that shouldn't be too bad. So yeah, given that formula, you just plug in everything. And yeah, on the PO, you evaluate divergence of f, which in this case gives you -2, which is less than 0. And so the whole integral is going to be less than 0, which gives you that e to the value of the integral is less than 1. So you have stability again.
Yes. Okay.
Yeah, and usually the keyword in a question, if they want you to use this method, is use the divergence test.
Oh, okay.
Or like, I mean, it'll have the word divergence in it. Yeah, so I think that's everything.
Yeah, nice.